but not
I
quad.
think that depends on like what kind of connection, what kind of connection they think you have.
Oh, really? The default?
Yeah, they'll default
Yeah.
you to whatever they think you can handle.
Okay, cool. All right, so so by and large, good job on the homework. I did not grade every single question. I picked 2 questions to grade, which I felt were neither too easy nor too subtle.
Actually, this one goes too.
Yeah. So, if you have questions about any of these, though, or you're not sure that you did these right or that you understand them, definitely ask. Okay. My original plan was to do weekly quizzes in here. I'm rapidly backing down from that plan, just from a time perspective and a cost-effectiveness perspective. I would rather spend time talking about the homework than doing quizzes. So I'm thinking I may do a few quizzes throughout the term, probably 3 or 4 quizzes. So I will not do a quiz tomorrow, okay? But I would like you to be sure that you understand the week 1 material, set theory, and stuff like that.
I did have a question on number 7.
Okay, cool.
Yeah.
7 was one of the ones I graded, so I'll definitely go over that too. So question 1 are basic set operations, and when I glanced at people's answers, that seemed fine. Question 2 was one I graded, so give specific examples where the size of this is equal to the size of this plus the size of this. So cardinality of A union B equals cardinality A union, cardinality plus cardinality of B, and most people were able to come up with examples. For example, A equals 1, 2, 3, and B equals 4, 5, 6. So the union is 1, 2, 3, 4, 5, 6, has 6 elements. This has 3, this has 3, 6 equals 3 plus 3. That's a fine example. A case where this does not happen, where this is not equal, would be something like 1, 2, 3, and 2, 4, 5. The union is 1, 2, 3, 4, 5 that has a total of 5 elements, but A has 3 elements and B has 3 elements, so 5 is not 3 plus 3. And how can you tell without evaluating each side of this expression? And it's basically, if the intersection of these 2 sets is empty, then this equation will be an equality. Because the exact equation that we talked about, which is always true, is this. You add a number of elements in A with a number of elements in B, but you subtract the number of elements that overlap. So if this is equal to the empty set, this is 0, and this is just equal to this. And conversely, if this is equal to this, then this must be equal to 0, which means A intersect B must be the empty set. Let me talk about the complements, because I think there's usually some confusion about this. So A is a set of all odd numbers, B is a set of numbers divisible by 5. So list 5 odd numbers that are not divisible by 5. That's all you have to do for A complement B. So 5 odd numbers that are not divisible by 5, 1, 3, 7, 9, 11. Those are each elements of A, which is odd numbers, and they're not, did I mess it up already? And they're not elements of B, which are numbers divisible by 5. B complement A should be multiples of 5, things that are divisible by 5 that are not odd numbers. So 10, 20, 30. Would be an example.
So B slash is complement there. It's the complement of the next term.
Yeah, it's the complement of this inside here, and you'll also see it written with subtraction sometimes. So start with this set, take away the things in this set.
But I thought B was only odd numbers because it's...
B is, oh, the set of A, you're right. I thought this was trickier than that. So this should be the odd numbers that are divisible by 5 that are not odd numbers.
So it's empty.
So this is empty. Thanks. All right, membership tables we talked about, and we did those last week. 3 sets with cardinality we talked about yesterday. Recurrence relation we talked about yesterday. Number 7. So this is a thought exercise playing around with these set operations. So our universe is 1, 2, 3, 4, 5. Those are all the things we consider for sets. And B has 2 elements, 2 and 3. And then you're asked to consider the following 2 situations separately. So in part A, we're told that the union of A and B is 1, 2, 3, 4. So what can we say about A? Since the union contains 1 and 4, but B does not contain 1 and 4, we know absolutely that 1 has to be in A and 4 has to be in A. So it's got to contain both of those elements. We also know something else.
That A doesn't have 5.
That A doesn't,
Have 5.
A does not have 5.
Or 2 or 3. Or, well, no, we don't know that.
Right, because if 5 were in A, then 5 would be in the union. But 2 and 3 could be in A or might not be in A.
It's really all we can say is A complement B is 1 and 4. And 5 is an A.
That's what you said, right?
I think that's what I
I
said.
was trying to think about that late at night. I think that's correct.
Pretty sure it's good.
Yeah.
So you want us to specifically address the elements are not in A?
I want to know anything that you can say about A, as much as you can say about A
Okay.
in this situation. So for example, A is a subset of U. We know that because it's part of the universe, but you can say more than that. We know that it contains 1 and 4, but you can say more than that. It does not contain 5. We know that's true also. I think that's all we can say about A, though. We don't know if it contains 2 or 3 or both or neither. And then in part B, if the intersection is 2, well, we know that 2 has to be an element of A, because otherwise it wouldn't be in the intersection. But we also know 3 cannot be an element of A, because if it were, then 3 would be in both A and B, would be in the intersection. And A could contain 1, it could contain 4, it could contain 5, and in either case, the intersection would still just be 2. So that's all we can say about A. It has 2, it does not have 3. All right, 8, universal set, infinite set. A and B are infinite subsets of U, and we talked a little about these last week also, or maybe on Monday. The complement of an infinite set could be finite, could be infinite. If U equals Z, the set of all integers, and A equals 2 times the set of integers, so it's all the even integers, then the complement, you take away A, that's all the odd integers, which are still infinite. But if A were equal to Z, then the complement would be empty, which is very finite. So the complement does not have to be finite. Must the union be finite? No, if A is infinite and B is infinite, their union is definitely going to be infinite. And the intersection of 2 infinite sets could be infinite, could be finite. If they're disjoint, the intersection will be empty, which is finite. If they're the same set, the intersection will be the same set, which is infinite. So intersection does not have to be finite.
So
Union is definitely not.
on questions like this, would it just be sufficient to I plan to give a counterexample on it, so it's like it doesn't have to be.
Only if I ask. But if you're working this in your head and you come to your answer by way of a counterexample, go ahead and put it down. Because if you just say yes or no and the answer is wrong and there's no explanation, I can't give partial credit. But if you put down an example, you might get almost all the points. But sometimes I'll say, if yes, say yes. If not, give a counterexample. And then do whichever. And then 9 we talked about yesterday. 12 elements, and you could think of it as combinations of sides of a coin and number on a 6-sided die. All right, so I will post another homework tonight for next week. So back to propositions. So I had put up an example. There's nothing particular about it. So we want to show that this side is equal to this side, and again, you can't just manipulate both sides. Let's start off with just this side. And by De Morgan's theorem, the negation of an or is the and of the two negations. So this is equivalent to not P anded with not P and Q. Negate both of those. So not this or this is not this, ended with not that. And this we can show is equivalent to, again, using De Morgan's theorem. Not this ended with this will be not P, ORed with not Q. And that's De Morgan's theorem again. And not P, that's a double negation, that's equivalent to P. So this is equivalent to negation of P ended with P or not Q. That's double negation. And did I call it distribution? This thing anded with this or this is the same as this anded with this, or this anded with this. I think that was back from Monday. So that's distribution. And not P anded with P is always false. So this is false, ORed with not P or not Q. And that's P and not P, that's negation. And we had a thing called domination. No, we had an identity, which said P or false is equal to P. And we've almost got that. We've actually got false or something. But we can say that this is equivalent to not P or not Q, or with F. That's commutivity.
The third line down, it's not P, no, the next one. It's not P and then, what?
P. So I did not P and P, and that's ORed with not P or.
Okay. Yeah.
Did I distribute wrong?
No, I think you got it.
Yeah, so I did not P and P, and then I ordered with not P. I think that's an and.
Yeah.
That's
Thank you. All right, so this ended with this, or this ended with this. So that's not P and not Q. Thanks.
So, why did the or in the parentheses change to the and on the second line?
On this one?
Yeah, the P, or not P and Q kind of.
So I did De Morgan's theorem on this piece. So all of this changed into all of this. So De Morgan's theorem says not A and B equals not A or not B. So we can flip this around by commutivity. And then when we OR something with false, we just get our expression back. That's identity. So let me move over to another page. So this is equivalent to not P and not Q. That's identity. Because we're ORing with false. And so from all of this, we've shown that this is equivalent to this, which is what we were trying to show. So you've got several of these identities, double negation, distribution, commutivity, and so on, and by using those you try to transform one side of your expression until it looks like what you're trying to show it's equivalent to. And we know all of these statements are true because we used theorems that we know give us equivalent statements. And at no point did we assume this was equal to this, or equivalent to that. So that's one example of a proof. Everybody got this? Yeah, we're good side. So quantifiers. So we have two quantifiers we talk about. This is the universal quantifier, and this is the existential. And we can think of this as basically saying for all. And we can think of this as saying there exists. And we can form propositions using these quantifiers. All right, can I erase?
Yeah.
So for all x contained in z, all integers, x is less than 0 or x is equal to the absolute value of x. That's a proposition. And it happens to be true. Every integer is either negative or it's equal to its absolute value. There exists an x contained in z such that x squared equals x. That's another proposition. That's also true. There's actually two integers that are, there's actually two integers that are equal to their square. Which are they?
1 and 0.
1 and 0. So those are true propositions. That happens to be a false proposition. Because there's no integer that's equal to itself plus 1. This happens to be a true proposition. And if I think of this symbolically, there exists an x in z such that, and this is a proposition, x equals x plus 1, I can just call it p. This is, for all x, negation of p. And this, these propositions are negations of each other. If you say there exists an x such that p is true, the negation of that is for all x, p is false. So we can flip between quantifiers by using negation. And the negation of this statement, for all x, x is less than 0 or x equals its absolute value, the negation of that would be there exists an x such that x is bigger than or equal to 0 and x is not equal to the absolute value of x. And this you can think about and convince yourself is clearly false. This is saying there is an integer which is not negative but is not equal to its absolute value. And that's not true. But this is the negation of this. And I slipped a Morgan in there. The negation of this or this is the negation of this and the negation of this. X bigger than or equal to 0 and x is not equal to its absolute value. And we do a lot of this in our heads without thinking about the Morgan's theorem and commutativity and all that. But we can make it rigorous like this. And when we do proofs, we're going to take our intuition and try to make it rigorous. We're going to say, well, obviously, if there's a number that makes this apply, then we can't say that for all numbers this isn't true. But we can make things mathematically rigorous, logically rigorous, using these kinds of machineries. But it's important when we do these that we pay attention. Yes?
Oh, when you're done, you
Go ahead.
So for your first statement, for all x that are integers, x is less than 0 or x is equal to its absolute value, is that statement by itself also implying that all negatives aren't equal to their absolute value, or does that need to be more explicit?
That does not say anything about the absolute value of negatives.
Okay. So it needs to be more explicit than that then?
If you wanted to say that, yes. See if I can think of an example like that. Right, I could say for all x, that's also a true proposition. The 12 is kind of superfluous.
Okay.
But if I say something like for all x, or there exists an x, that's a false proposition. There's no integer whose square is 2, but if I had done this, it becomes a true proposition. So you got to pay attention to the domain, the set over which you're considering these things, the universe. And if it's not explicitly specified, it's got to be understood, or come up to me and say, hey, you didn't tell us what the universe is. Because otherwise you can't answer. And let me mention one more version of a quantifier that again we'll encounter when we do mathematical induction. So for all x contained in natural numbers, which is 0, 1, 2, 3, 4, for all x contained in n, p of x. So p of x is a proposition that takes a propositional variable, a logical variable x. For example, p of x is the proposition 2x equals x plus x. So p of 5 is a proposition which says 2 times 5 equals 5 plus 5. P of 1,000,000 is a proposition that says 2 times 1,000,000 equals 1,000,000 plus 1,000,000. And we have a family of propositions here that we just call P of x. And we can use an expression like this for all x in the natural numbers, P of x. Which means P of 0 is true, P of 1 is true, P of 2 is true, P of 3 is true, and so on. So this is equivalent to ANDing all of those propositions. Use the existential quantifier, there exists an x in the natural such that P of x. That's equivalent to saying there's some number, at least one number x, where P of x is true. And since x ranges over the naturals, this means either P of 0 is true, or P of 1, or P of 2, and so on. One of those at least has got to be true. And this will be where we get mathematical induction from in another week or so. And we can nest these quantifiers so all of these will be working over Z. So for all x, there exists a y such that x plus y is 0. So these go left to right. For all x, or any integer x, we can find a y such that x plus y equals 0. Is that true?
Yes.
Absolutely. We can just set y equal to negative x.
What's Z again?
What's what?
Z.
Integers.
Okay.
Yeah.
And where are you reading the such that from in this statement?
That's just parentheses.
Okay.
So for all x, there exists a y such that x plus y is equal to 0. So that's true. There exists a y such that for all x, x plus y is equal to 0. So what is that saying?
Wait,
There exists a y such that for all x, x plus y is equal to 0.
there's no number. It's basically saying all possible x's, x plus y equals 0.
Right, it's saying there's some magic number y that anything you add to it gives you 0.
But instead of plus, if it was like 1 plus, that could be 2.
But there exists a y such that for all x, x times y equals 0. That's certainly true. The magic y is 0. There exists an x and there exists a y such that x equals y. That's clearly true. Y can just be equal to x. For all x and all y, x is equal to y. That's false, unless we only have one number. For all x, for all y, xy equals yx. That's true. That's commutativity of multiplication, and so on.
So the for all x for all y x equals y, that could be true if the universe was 1,
If
right?
you only had one number,
Yeah.
yeah.
Okay.
So if we were over a universe of 1, right? Or if we defined equality differently so everything was equal. All right. That's enough of quantifiers. Let's go on to the good stuff. We'll do good stuff for the rest of the week. So, rules of inference. So if it's sunny, then I'm on a run. That's a proposition. And I'm telling you that that's true. It's not sunny right now. And if it were sunny, I'd be out running. Skip class, no. If it's sunny, then I'm out on a run. Okay? Here's another proposition. It's sunny. If this is true and this is true, what can we conclude? I'm on a run. If this is true and this is true, therefore, I'm on a run. And we want to study how we can formally validate this reasoning. And so these are called rules of inference. And this is a proposition, and this is a proposition, this is a proposition, this is a proposition. And if-thens, we call those conditional statements. And so we can rephrase this as saying, if P, then Q. That's that first proposition. The second proposition is P, and our conclusion is therefore Q. So if we know this is a true proposition, and we know this is a true proposition, we're forced to conclude that Q is also a true proposition. And it's got to be that way from the way we understand logic, because it's sunny, and this says if it's sunny, I'm on a run, so it's going to be on a run. This says P is true, this says if P is true, Q is also true, so Q's got to be true. Okay, we know that intuitively from working with logic and language and such, but we can formalize that by saying modus ponens. That's the name of the rule of inference, which says that's valid. And I switched textbooks last year, and the online text uses different terminology. So instead of the fancy name modus ponens, they call this detachment. And they don't seem to use Latin in that text, so this is called detachment.
So are you just using modus ponens or detachment as a justification for saying that Q is true?
Correct. Yeah, modus ponens is the statement that if this is true and this is true, then Q is true. And we can generalize this if we know if A then B, and we know if B then C, and we know if C then D, and we know if D then E, and we know all of this up to and including if Y then Z. And if after all of that we also know A, so let me just put all that is true, and if A is true, then we can conclude that Z is also true. And this would take 26 applications of modus ponens. We'd say A, if A then B, and A, therefore B. And then we'd say if B then C, and B, therefore C, and so on. So to write this out formally would take you 26 lines. But to prove this using truth tables, you've got 26 variables in here. You would have 2 to the 26th rows. That's 32 million rows in your truth table versus 26 lines of logic. So this will get you there a whole lot quicker often. Truth table proofs are sort of brute force, just bang through all the possibilities, but they don't really rely on any sort of logical insight. And this is more relying on logical insight, which means these are not a slam dunk to do. Truth tables, you can write a program to fill in the entries and then confirm that 2 columns are the same. This takes more insight, but it's more fun once you get the hang of it. So I believe pages 58 and 59 in the online text list a variety of rules of inference, and we'll talk about these, but I'm not going to spell them all out in detail. But we'll put some of them up and we'll talk about some examples. And we have like 2 minutes to start with that. But that's one example, modus ponens or detachment. P implies Q and not Q, therefore not P. And the book calls this indirect reasoning. Or modus tollens. If I'm a dog, then I like bacon. I don't like bacon. Therefore, I'm not a dog. So this is P, this is Q. If P, then Q, not Q, therefore not P. And that's always going to be true. Because if this were not the case, if I were a dog, this says I must Q, and this is saying I don't Q. So this is always logically correct. And so what we're going to do starting tomorrow is we're going to come up with a series of propositions and then ask a question, if I'm going for a run, am I a dog? And from what we know and from using different rules of inference, we'll try to take what we know and derive from that what we're asked to show, or the contrary of it, in which case we can prove that the conclusion is false. So that'll be logical reasoning. We will do that tomorrow, and that will leave us with nothing else in this chapter except some proofs. So we'll finish by talking about even and odd numbers and working through some proofs using some of these ideas. And that may go on into next week. I will post some homework later today, and we'll talk about it tomorrow.
No quiz tomorrow?
No quiz tomorrow. Quiz-free Friday.
Okay, now that's been straightened out.